Welcome back, and so in this video we're going to look at the general term or the nth term of a geometric sequence. This is also known as a geometric progression. So we're going to look at how we derive the nth term and also what actually defines a geometric sequence compared to an arithmetic sequence. Now the four questions that I'm going to go through are illustrated here. If you want to pause the video and take a screenshot and work through them at your own pace, then please do so. They get progressively sort of more challenging, I believe, as we work through, and they each require a slightly different approach. So just be careful, each one is a slightly different technique. Let's dive in. Okay, so let's briefly go over the general term and how to derive it, also known as the nth term. So have a quick look at this sequence that I've got here, 2, 4, 8, 16, 32. It's quite a simple sequence. You can see that it's being multiplied by 2 every term. So that is actually what we call the common ratio. So when we take one value and divide it by the previous value, so in this scenario, this is u1, and then this is u2, and this is u3 and u4. When we take one term and divide it by the previous, we're going to get u2 divided by u1 would equal 4 divided by 2, which is 2. Okay, so 2 is known as the common ratio, right? So that's quite important. Some people get that mixed up and would say it's a half and divide the wrong one, but it's increasing by 2, like a factor of 2 every time. So we're multiplying by 2, okay, and then we're multiplying by 2 again, so that is our common ratio. Now, if we look at this sequence again, but a little bit more in depth, so if we've got 2, 4, 8, 16, and 32, now let's think about labeling the first term up as u1. Well, the second term then was found by taking u1 and multiplying it by r. Now, if we wanted to go from 4 to 8, we're going to have to times by r again, so that's why we get u1 times r squared. And this just keeps repeating, so the next term would be u1 times r cubed. Now, if you remember what I said, that this was actually term 1, and this was term 2, this is term 3, and term 4, we can analyze, and we can sort of, through inspection here, realize that the term number is always 1 greater than the power of r. Okay, so this is where our general term comes from, that if we want to find a general term in the sequence, un, then it will always be u1 multiplied by r, but then the power of r must be 1 less than the term that you're looking for. So that's where the general term or the nth term formula comes from. We're going to use that in the following questions. Okay, and another quick note here, that the common ratio r is always equatable to if you have two subsequent numbers divided by one another. So if, for example, if you had u2 divided by u1, that would result in r, but so would any other two consecutive numbers. So for example, you had u5 divided by u4, that would also result in r. The reason being is let's just take this one, for example. If u2 was u1 times r, and we divide it by u1, then these will cancel out, leaving r. And that is the same for, let's say we had u5, so that would be u1 times r to the power 4, and we divide it by u4, that would be u1 r cubed. Well, the u1s will always cancel out, and all these r's will cancel out with these, just leaving with r. So that's why we always get that sort of scenario, that they are always equal to the common ratio if you divide consecutive numbers in the sequence. Okay, on to question 1. Consider that the sequence 8, 4, 2, 1.5 and show that the sequence is geometric. Right, so we just need to prove this then. We need to show that u2 divided by u1 is equal to 4 over 8, which is a half. Now that should be true for all consecutive terms of the sequence. So let's go ahead and do it for the next two. So that's going to be u3 divided by u2 would be equal to 2 over 4, which is also a half. And this is just going to keep repeating. So let's just try one more. We're going to say that u4 divided by u3 is going to be 1 divided by 2, which is equal to a half. And we can see even from the last one, which I won't do, it would be the same. A half divided by 1 is also a half. So that's our common ratio, a half. Now it says find the general term un, right? So this means then that the general term, as we saw in just the previous sort of slide, that it will always start with u1, and it will be the common ratio r, but always to the n minus 1. So let's go ahead and plug in what we do know. We know that the first term of the sequence is this term here, which is 8. So we've got 8 times r. Now that's our common ratio, so try to keep that in brackets, especially if it's a fraction, or and then this is to the n minus 1. Now you don't ever put in anything for the n minus 1 because this is the general term. So we want to use this if they're asking us to find any specific term of the sequence, but we have answered part B in that problem. Okay, let's go back up and look at C. Hence, find the 12th term as a fraction. Right, so 12th term as a fraction will be u12, so term 12 will be 8 times 1/2 to the power of 12 minus 1. So that's actually 11. So let's just write that down. So u12 is equal to 8. Now, when we have something like a fraction raised to a power, don't forget your rules of indices are that you can raise this 1 to the power of 11 and also this 2 to the power of 11. So I'll just write another line down there then, that u12 is equal to 8. Now 1 to the power of anything is still 1, so that's just 1, over 2 to the power of 11. And that's quite a large number, so what you can do if you spot that 8 is actually 2 cubed, and that is over 2 to the 11, so you can cancel some of these 2's with the ones on the bottom. So therefore then that is the same as saying 1, okay, over 2 to the power of 8, and that's where we get the final answer is 1 over 256. Now don't worry if you found that last little bit tricky, that's just a bit of number work at the end that they've thrown in there. Okay, question 2. So we have 3 consecutive terms of a sequence, but we don't know exactly what those terms are. They're in terms of k, as we can see on the left here. They're geometric, so find k. Right, okay, so do you remember a few slides ago I said that if we take one term of the sequence and divide it by the previous term, then that is the common ratio r. So therefore then, in this one, if I can do these two in a sort of a fraction, I can also do those two because they're also consecutive. So what we'll do here is I will write that that is equal to 21 minus k all over 2k. And I can see what's going to happen here. We're going to end up getting some sort of quadratic to solve. So let's multiply, cross multiply. Okay, we're going to get 4k squared is equal to 21 minus k multiplied by k minus 1. Let's leave the 4k squared just for a moment. So we've got 21 So you can do this in your way, but that's just the way that I'm happy with. So now I just need to factorize this up. So this is going to be 5k, open brackets, close brackets, k, close brackets, and we need to look for two numbers that times together to make minus 21, and that's going to be minus 7 and negative 3, because in a lot of these cases you will need to factorize a quadratic up. Now we look at these two brackets, so we want to equate both to 0, so either 5k minus 7 is equal to 0, therefore 5k is equal to 7, so k is equal to 7 over 5. Okay, there's one result. Or, okay, k minus 3 has to equal 0, or k is equal to 3. And that is the end of that question. There are two possible results for k. Question 3. So we have a geometric sequence with a second term and a fifth term given. Find the general term. Okay, so this is also another common style question. So what we're going to do here is if we write out that u5, right, is equal to u1 times r to the n minus 1, which is 4, then what we can do here is we also know the number for u5, right? We also know what value that is equal to. That's 162. So what we often do here is we can say, well, let's say we take u5 and we divide it by the second term there. That means the second term, which is now in yellow, will be u1 times r, and the second term is also equal to negative 6. right? So what I'm going to do here is I can cancel the u1s out. I can cancel one of the r's out, making that 3. So this whole expression in this comes just down to be r cubed. But now we have 162 over negative 6. And what we can do with our calculator is we can just cube root both sides. So when we cube root the left-hand side, the cube root and the cube will, cancel, but we must cube root the right-hand side as well. Another way is just saying we raise it to the power of a third, or raise it to the power of a third. It's the same meaning. It's actually the same operation. Okay, so I'm going to cube root both sides. So we get r, and now we just need to figure out what the cube root of 162 over negative 6 is. So I'll just punch that into my calculator now.
A few moments later.
And that comes out to be negative 3. Okay, so now it does ask us to find the general term, and if the general term is un is equal to u1 times r to the n minus 1, there's a slight issue because we don't have u1 at the moment, but we do know r. So we're just going to find u1. Now that's relatively simple because we can use the value for u2, so let's just section this off here. We were told that u2 was equal to negative 6, but u2 is actually u1 times r, and that's minus 6, and we just found that r is minus 3, so u1 is negative 3 times, is equal to minus 6. Divide both sides by minus 3, so u1 is 2. Right, so now we can go ahead and find the general term. I'll do that in a nice clear white here. The general term is u1, which is 2, times r, which is minus 3, to the n minus 1. And there we go. We have finished that question. We have found the general term when they gave us 2 terms of that geometric sequence. Okay, on to question 4, and this one is a slightly different approach. We're actually going to need our graphical calculator or some kind of calculator at the end here. Because it makes it a little bit tricky when they ask us this style of question. Find the first term of the sequence which exceeds the value 1,400. So this sequence is growing. Okay, so going 6, then it's 6 times root 2, and then it's 12, and then it's 12 root 2. Now, some of you might be able to spot r, the value, the common ratio straight away, but if you're not sure, just remember, take one term and divide it by the previous term. So we've got 6 root 2 over 6. That means root 2, so this will be r, and that is just going to be equal to root 2. So the common ratio between the terms is root 2. So what we have now is if the general term is un is equal to u1 times r to the n minus 1, well, the first term of the sequence was 6, right? And r is root 2, we just established that, and this is to the n minus 1. Now we want to know when this term exceeds, is larger than 1,400. So what we do in many of these cases is we'll set up an inequality here. We want to know when this term exceeds 1,400. That's what we're doing. Now I'm going to jump over to my calculator and show you 2 possible techniques of how to solve this. Okay, so technique number 1 is to use logs. So what we can do is we can say that, imagine that the term is actually equal to 1,400 at some stage. Therefore, then you would have this setup. Now, it's very unlikely it'll equal 1,400, but it may do, but we can say that, assume it does. So we can use logs to help us solve this. So we're going to divide both sides by 6. So we've got 1,400 divided by 6 is equal to root 2, n minus 1. And that is going to be 700 divided by 3. And what we're going to do is if we take logs of both sides, then we'll be able to bring down the n minus 1. So when we do that, we're going to take log. Now, I'm just going to write 10. I'm just going to use base 10, but it doesn't matter which log you use, actually, as long as it's the same on both sides. But base 10 is the standard. So we'll just use log to base 10 on this side of root 2. And, the n minus 1 will come down. So let's put that in a slightly different color so you can see it there. Now I'm going to divide both sides by this log root 2. So dividing both sides by that, we're going to get log. I'll just drop the base 10 for now, just to keep it a little bit cleaner. And dividing both sides by log root 2. And don't forget, this is equal to n minus 1. So instead of writing all that out again, what I'm going to say is I'm going to add 1 to both sides. When I add 1 to both sides, this will just drop down to n. So we'll do that now. So that's summing 1 to both sides. That means we will have to add 1 to this side. There we go. So if I just go ahead and put all this into my calculator, I should get some kind of result, and we'll go from there. Okay, so I've just typed all of that into my calculator. It doesn't matter if you have a graphical calculator for this one, you can use a regular one, and that matches exactly what we saw. So I'm just going to press enter, and we get a value of 16.7. Now, what does that actually tell us? Remember, we were setting up that this sequence was equal to this value. Now, we can't have a decimal in the term number. So if n is equal to 16.7, that means then at term 16, the value is not quite at 1,400, but at term 17, the value will be exceeding it. So this is why we all jump over to n is 17 now, because if you remember, the original inequality was set up that when would this value exceed that value? So we'll have to move in integers. So moving in integers would mean that it would be 17, because that's the first integer greater than 16.7. Now, the other technique, if you have a graphing calculator, is to graph the function. So what you can do here is I just typed it into the command bar, the actual geometric sequence. So that was the first term, but that was the common ratio. But this time I didn't put n minus 1, I put x, because the variable on the x axis is x, so I don't want to put anything that the calculator won't understand. Then I graphed it, right? So we get this graph. Now what we can do is we can also input a second function, and this time 1,400, and press enter. Now we don't see that because it is way off the chart, so I'm going to double click my axis here and just put something larger than that value so we can see it. And it is also slightly off the chart to the right, so let's just go over to, let's put 20 in. And now we can see the intersection of the two. So what I can do is I can find that intersection by going Menu, Analyze Graph, and Intersection. And if we find that intersection there, we can see that the value is 16.7, similar to that one we did the log. So therefore, the next integer larger than 16.7 would be 17. And that is a second approach using a graphing approach to find that answer to that question. Okay, geometric sequences. Would you like me to go through more examples? Do you want me to go through some exam questions? How do you find them? Please leave me a comment below. Don't forget to like and subscribe to the channel, and I'll see you next time.